Welcome to this final sub-module 3 of 3 on deflection methods. At the end of this module, you should be able to demonstrate 3 things. First, you'll be able to list the 4 main deflection methods used in directional drilling: whipstock, jetting, steerable positive displacement motors, and rotary steerable systems. Second, you'll learn how controlled deflection is actually achieved in each case. That means understanding not just the tool components, but the mechanisms, whether it's the face of a whipstock guiding the bit, the hydraulic power of a jet spudding a pocket, the bent housing of a motor creating curvature, or the electronic control of a rotary steerable tool adjusting trajectory while rotating. Finally, you'll examine the advantages and limitations of each approach. No method is universal. Formation hardness, well complexity, cost, and operational risk all influence the right choice. By articulating these trade-offs, you'll be able to explain why a whipstock might be selected offshore for casing exits, why jetting is confined to soft formations, or why rotary steerable dominates in extended reach wells. These objectives provide a clear framework: know the methods, know how they work, and know when they are best applied. With that roadmap, let's now explore how we can deflect a well path in practice. The steerable positive displacement motor, PDM, quickly became the standard deflection tool after whipstocks and jetting. The most common design is the single bent housing motor, where a slight bend, typically between 0.5 degrees and 3 degrees, is built into the housing above the bit. The assembly alternates between 2 operating modes. In slide mode, the drill string is held static while the motor turns the bit, allowing controlled curvature in both inclination and azimuth. In rotate mode, the entire drill string rotates, behaving like a conventional rotary assembly and drilling straight. By alternating between sliding and rotating, operators can steer a well to its target with precision. A typical steerable motor BHA includes the bit, the PDM, and a float sub. A collar of non-magnetic material and/or a stabilizer is connected to an MWD tool, enabling surveys. The stabilizer helps build control. Steel collars, jars, and heavyweight pipe extend the assembly. The steerable PDM is versatile. It can be used for kickoffs, correction runs, side tracks, and complete hole sections. Its main limitations are reduced sliding efficiency in long horizontals, poor hole quality due to repeated slides, and a lower rate of penetration compared to rotary steerable tools. Still, it remains a cost-effective, reliable, and widely used tool for directional drilling worldwide. The shorter the distance from bit to bend, the higher the dogleg capability. Also, the greater the adjustable bend, the higher the dogleg capability. The trade-off is that as the adjustable bend increases, the maximum RPM at which the string can be rotated is reduced due to fatigue. Steerable motors operate in 2 distinct modes. In oriented slide mode, the drill string is held stationary while the motor rotates the bit. This allows the bend in the housing to create curvature in the desired direction. Slide drilling gives precise control over inclination and azimuth, making it ideal for building angle or correcting trajectories. However, it comes at a cost. Hole cleaning suffers due to a lack of drill string rotation and increased tortuosity. In rotating mode, the drill string is rotated from the surface, straightening the assembly and drilling much like a conventional rotary system. This produces a smoother in-gauge hole with better hole cleaning and faster ROP. Directional control is limited and the borehole often ends up slightly over-gauge because of bit offset. The real strength of steerable motors lies in alternating between sliding and rotating, giving flexibility to deflect when required and drill efficiently otherwise. The balance depends on the well design. High dogleg sections demand more sliding, whereas tangent or horizontal sections emphasize rotation. Understanding when and how to switch between modes is critical to maximizing efficiency and maintaining hole quality. Turbo drills, or turbine motors, use stacks of vaned rotors and stators to convert hydraulic energy directly into bit rotation. They operate at very high speeds, often up to 900 RPM, making them especially effective in hard, abrasive formations when paired with natural diamond bits. The downside is their high pressure drop, around 1200 psi across the tool, which must be carefully balanced with hole cleaning requirements. Turbo drills offer a smooth, vibration-free rotation compared to steerable motors, and some designs are elastomer-free, making them suitable for high-temperature wells or multi-phase fluid environments, such as underbalanced drilling. They have historically seen extensive use in Russia and high-temperature reservoirs. However, their uptake elsewhere has been limited due to complexity, higher operational demands, and the dominance of steerable motors and rotary steerable tools. Also, PDC bit technology has improved, increasing the envelope of hard rock applications. PDC bits tend to be significantly cheaper than impreg bits and are run with PDM or RSS. In practice, turbo drills remain valuable for niche applications where their high-speed, reliable cutting action provides a clear advantage. Think of them as a specialist tool, less common globally, but unmatched in certain hard rock or high-temperature scenarios where conventional elastomer-based motors would fail. Rotary steerable systems, or RSS, represent the most advanced evolution of deflection technology. Unlike steerable motors, rotary steerable allows continuous steering while the entire drill string rotates. This solves many problems associated with slide drilling, including improved hole cleaning, reduced torque and drag, and the production of smoother in-gauge well bores. The benefits of RSS are significant: better well placement, especially in complex geologies, extended reach drilling in long horizontals, steadier deviation control, and real-time azimuthal formation evaluation while drilling. These advantages translate directly into improved performance, including higher rates of penetration, reduced wiper trips, and enhanced hole quality, resulting in faster and lower risk completions. The main drawbacks are cost and complexity. RSS tools are expensive to run and require specialized support. They may also struggle in certain complex formations. However, in high-value wells, such as deep water, geosteering, or extended reach projects, the investment is justified by the reduction in drilling time and improved reservoir contact. RSS has become the system of choice in many major operators' drilling programs, setting the standard for modern directional drilling. There are several mechanisms by which RSS achieves deflection. The push-the-bit design uses pads that extend from the tool's side to press the bit laterally against the borehole, nudging it in the desired direction. The point-the-bit design deflects an internal mandrel, effectively pointing the bit at an angle while the drill string rotates. Each approach has its advantages. Push-the-bit tends to be simpler and cheaper, while point-the-bit provides higher doglegs and smoother hole profiles. Some tools combine both, creating hybrid systems that can adapt to different drilling environments. There are also permanently deflected bit systems, such as SLB's PowerDrive Exceed and XL, which hold a fixed deflection, and fully articulated hybrids like the SLB Archer tool. The most recent innovation is at the bit steering, such as the SLB NeoSteer tool, which places the steering mechanism directly at the bit for maximum responsiveness. The choice of mechanism depends on well objectives, formation type, and operator preference. The takeaway is that RSS is not a single technology, but a family of solutions, each tailored to optimize control, hole quality, and efficiency in different scenarios. The picture below shows the 4 types of RSS tools as classified by the IADC. Case 1 is the push-the-bit tools that cause deflection of the well path through side force, even if this results in bending of the tool body, as with auto-track. Case 2 is point-the-bit. These have a central shaft which is deflected, causing the bit tilt and therefore pointing the bit. Case 3 has a permanently deflected shaft which points the bit tool. The tool is always pointing, which means that when not steering, the bit orients in a manner to deliver a neutral directional response. Case 4 is the hybrid tools that use articulation of the body of the tool. Instead of having pads that push out to the formation, as with Case 1, the pads push inward onto a shaft to deliver a bit tilt. Let's revisit the learning objectives to consolidate what we've covered. First, you should now be able to list the four main deflection methods: whipstock, jetting, steerable motors or turbo drills, and rotary steerable systems. Second, you should understand how each achieves controlled deflection, whether by mechanical wedge, hydraulic jetting, bent housing motors, or electronic pad and mandrel systems. Third, you should be able to state the advantages and limitations of each. Whipstocks are reliable in casing exits but less efficient in open holes. Jetting is simple but limited to soft formations. Steerable motors are versatile but slower and rougher than RSS. Turbo drills excel in hard rock but are a niche product. RSS delivers the smoothest and most efficient drilling but comes at a high cost. The important point is that no one method is perfect. The right choice depends on lithology, economics, and well objectives. Having explored each, you should feel confident comparing options and explaining why a certain method is chosen in a given scenario. That brings us to the end of the module. Thank you for watching this module on deflection methods. Please progress to the quiz.